All right, let's get into it. Today we've got a real scientific detective story for you. We're talking about a huge mystery right at the very heart of quantum physics. And the weirdest part? The clue that cracks the whole case, it doesn't come from a physicist in a lab. Nope, it comes from a philosopher. So picture this. It's the early 1960s, and quantum mechanics is on top of the world. I mean, it's basically seen as the perfect theory, a total triumph for science. But here's the kicker. While all the physicists are taking their victory laps, there's a fundamental crack in its foundation. And the first person to really shine a light on it? Not a physicist. So Section 1, a crack in perfection. You know, to really get why this crack was such a big deal, you first have to understand just how perfect the building was. Back in the mid-20th century, quantum theory wasn't just some new idea, it was the rulebook for the entire microscopic world. And I mean, just look at its track record. Quantum theory explained everything. The structure of atoms, why chemical bonds happen, how lasers work, even the bizarre behavior of superconductors. It was so good, one physicist famously joked, "Now we can eat chemistry with a spoon." It just made sense of everything. But right in the middle of all this celebration, a young, sharp philosopher named Hilary Putnam spots something. A huge problem. And it wasn't buried in some crazy complex equation. No, this flaw was hiding in plain sight, in the most basic thing you could possibly do. Just measuring something. And that brings us right to the heart of this mystery, the observer's paradox. This is the puzzle that's so famous, it's often just called the quantum measurement problem. And it all kicks off with something super weird about the quantum world. Okay, let's walk through this with a classic example. An electron's spin. So before you go and look at it, the electron isn't spin up or spin down. It's both. It's in this weird fuzzy state of all possibilities at once. We call that superposition. But the very instant you measure it, poof, that blurriness is gone. It just snaps into one definite reality. It's either up or it's down. It's never both once you look. So that's the big question, right? What on earth is happening in that moment of measurement? What is this force or this process that makes that whole world of fuzzy possibilities just collapse into the single solid reality we see every single time? Well, the brilliant mathematician John von Neumann laid out the logic, and honestly, it's going to bend your brain a little. So the particle starts in superposition. Fine. It then interacts with the detector. But according to the rules of quantum mechanics, that means the detector now has to be in a superposition too. Okay, then the detector's signal hits your eye, so now your eye is in the superposition. That signal travels to your brain, and wait, does that mean your brain is now in a superposition of seeing up and seeing down at the exact same time? The weirdness just keeps spreading out, like a ripple. So what could possibly stop this runaway chain of quantum weirdness? Von Neumann and later the Nobel Prize winner Eugen Wigner, they came to this absolutely wild conclusion. The only thing that isn't part of that physical quantum chain, the only thing that could stand outside of it and break it, is consciousness itself. Yeah, the idea was that our non-physical mind literally steps in from the outside and forces a choice, basically creating reality by looking at it. And this is exactly where our philosopher, Hilary Putnam, springs his trap. He says, okay, fine, let's take that logic and apply it to the whole universe. The universe itself is just one giant quantum system, right? So if it needs an outside observer to collapse it into existence, well, who is outside the universe looking at it? Nobody. The whole argument just hits a brick wall. This debate, it went on for years. Wigner, Putnam, all these brilliant minds going back and forth. But here's the crazy twist in our story. The entire argument, this whole famous clash of ideas, was actually based on a massive misunderstanding of the evidence. A key clue had been sitting there the whole time, completely overlooked. See, the truth is, most of the physicists in this debate weren't actually reading von Neumann's original work, which, to be fair, was incredibly dense and in German. No, they were all referencing this little booklet that they just assumed was a simple summary of his ideas. But they were totally wrong. The real source was a booklet from 1939, written by two physicists, Fritz London and Edmund Bauer. And here's the hidden clue that changes everything. One of the authors, Fritz London, wasn't just a physicist. He was deeply into a school of philosophy called phenomenology. Nobody caught this. And believe me, it changes the entire story. So this brings us to a whole new way of looking at the problem. through the lens of phenomenology. What is this forgotten philosophy, and how does it crack this case wide open? Okay, so in a nutshell, phenomenology isn't asking what is the world really made of. Instead, it asks a different question. How do we experience the world? It puts the relationship between our conscious experience and the thing we're experiencing right at the very center of the picture. It's a complete shift in where you start. And this slide just lays it out perfectly. The classic view of science, right, is that the world is this objective thing out there, and we're just separate little observers looking at it from the outside. But the phenomenological view, it says, no way. That separation is an illusion. It argues that consciousness and the world are woven together. They're not two separate things that bump into each other. They literally co-create each other in a relationship. All right, so what happens when we take this new way of seeing and apply it back to that pesky quantum measurement problem? Well, something amazing happens. It doesn't just give us a new answer. It makes the entire original problem just dissolve. And this is the absolute key difference. Remember von Neumann's view? He put consciousness outside the physical world, like some magical trigger that causes the collapse. But London and Bauer, with their phenomenology background, did the complete opposite. They argued that consciousness is the final link inside the chain. It's not some external force. It's the natural endpoint of the entire process. So here's how they saw it working. First, the observer and the thing they're observing get linked up in a single quantum superposition. It's a state of relationship. Then comes the most important step, introspection. That's the moment the observer has the thought, aha, I have now seen the results. According to this view, that conscious act of self-awareness is what cuts the quantum chain. It makes the result definite for the system, and it creates a definite piece of knowledge for the observer, all at once. So you see what happened? The old problem just vanishes. It turns out we were asking the wrong question all along. It was never about what causes a mysterious physical collapse. The real question is much deeper. How do we, as conscious beings, participate in reality? And this idea, wow, it wasn't just some historical footnote. It was like a seed that was planted, and it lay dormant for decades, only to sprout up again in some of the most advanced, cutting-edge thinking in physics today. Just look at this timeline. It really shows the journey of this lost idea. You have London and Bauer back in 1939. Then, fast forward to the 2000s, and a totally new theory called cubism shows up. Now, cubism basically says quantum mechanics isn't a description of the world. It's more like a user's manual for how we interact with the world. And what are physicists realizing today? That cubism has these incredibly deep roots that go all the way back to that forgotten phenomenological insight. So, what's the big takeaway from our whole detective story? It's really this incredible shift in perspective. Maybe, just maybe, quantum mechanics was never supposed to be this cold, detached, third-person description of a world out there. Maybe, from the very beginning, it's been a theory about our fundamental relationship with the world. And that leaves us with one last huge question to chew on. Is the point of science to create a perfect, objective map of a world that exists totally separate from us? Or is it to tell the most accurate, structured, and useful story possible about our inescapable relationship with that world? The answer to that, well, it could change how we see science itself.